Download this code from codegive.com, link in the description below. Cost remains an issue, a deep dive into optimizing your code for efficiency and scalability. Cost optimization in software development is a multifaceted issue that goes beyond just the upfront cost of hardware and software licenses. It encompasses everything from the resources consumed by your application, CPU, memory, storage, network bandwidth, to the human hours spent on development, maintenance, and infrastructure management. As applications grow in complexity and user base, neglecting cost optimization can lead to significant financial burdens and hinder scalability. This tutorial will explore the various aspects of cost optimization in software development, offering practical strategies, code examples, and best practices to help you build efficient and cost-effective applications. We'll cover 1. Understanding cost drivers * identifying the key factors contributing to your application's cost. 2. Optimization strategies at different layers * techniques for optimizing code, database interactions, infrastructure, and development processes. 3. Code optimization techniques * focusing on algorithmic efficiency, memory management, and concurrency. 4. Database optimization * optimizing queries, schema design, and database infrastructure. 5. Infrastructure optimization * leveraging cloud services, containerization, and serverless architectures. 6. Development process optimization * adopting agile methodologies, automation, and code reviews. 7. Monitoring and measurement * establishing key metrics and tools to track performance and identify areas for improvement. 8. Case studies and real-world examples * illustrating the impact of cost optimization through practical scenarios. 1. Understanding cost drivers. Before diving into specific optimization techniques, it's crucial to understand the factors that contribute to the overall cost of your application. These drivers can be broadly categorized as compute resources * CPU usage, memory consumption, and storage space utilized by your application. This is especially relevant in cloud environments where you're billed for resource consumption. Network bandwidth * data transfer costs, especially for applications with high traffic or data-intensive operations. Database costs * storage, I/O operations, and licensing fees associated with your database. Infrastructure costs * servers, virtual machines, load balancers, and other infrastructure components required to run your application. Development costs * salaries of developers, QA engineers, and DevOps personnel. Maintenance costs * effort required to maintain the application, fix bugs, and deploy updates. Downtime costs * lost revenue and reputational damage caused by application outages. Third-party service costs * fees for APIs, SDKs, and other services integrated into your application. 2. Optimization strategies at different layers. Cost optimization requires a holistic approach, addressing inefficiencies at various layers of your application stack. Application layer * code optimization, caching strategies, and efficient data processing. Database layer * query optimization, schema design, and database indexing. Infrastructure layer * cloud resource management, containerization, and serverless architectures. Development process * agile methodologies, automation, and code reviews. 3. Code optimization techniques. The code you write directly impacts the performance and resource consumption of your application. Here are several code optimization techniques. Algorithmic efficiency * choose algorithms with optimal time and space complexity for the task at hand. In the above example, The find underscore duplicates underscore quadratic function has a time complexity of O, n caret 2, because it uses nested loops. The find underscore duplicates underscore linear function uses a set, which allows for O, 1, average case lookup, resulting in an overall time complexity of O, n. Choosing the correct algorithm can significantly reduce execution time, especially for large data sets. Memory management avoid memory leaks, release unused resources promptly, and use data structures efficiently. While Python has automatic garbage collection, understanding how circular references can create leaks and knowing how to explicitly manage resources, example closing files, releasing database connections, is important. gc.collect is generally not needed but shown for illustration. Caching store frequently accessed data in a cache to reduce the number of expensive operations, example database queries, API calls. The @functools.ru _cache decorator provides a simple way to cache the results of function calls. The maxsize argument controls the number of recent calls to cache. Subsequent calls with the same arguments will retrieve the result from the cache, significantly reducing execution time. This is a great example for memoization. Concurrency use multithreading or multiprocessing to parallelize tasks and improve performance on multi-core processors. Be mindful of the global interpreter lock, GIL, in Python, see below. Asynchronous programming, async/await, can also improve performance. The threading example demonstrates how to run tasks concurrently. However, Python's global interpreter lock, GIL, limits true parallelism for CPU-bound tasks. For I/O-bound tasks, threading is usually suitable. For CPU-bound tasks, multiprocessing is often preferred, as it uses separate processes, bypassing the GIL limitation. The async/await example uses coroutines, which allows for non-blocking I/O operations, improving responsiveness. Lazy loading load resources only when they are needed, rather than loading everything up front. In this example, the large object only loads its data when process_data is called. This avoids unnecessary memory consumption if the data is not actually used. Code profiling use profiling tools to identify performance bottlenecks in your code. The C profile module allows you to profile your code and identify which functions are taking the most time. This information can help you prioritize optimization efforts. After running the code, it provides details about the execution time and number of calls for each function. String concatenation use efficient string concatenation techniques, especially in loops. Repeatedly concatenating strings using the += operator creates new string objects in each iteration, which can be inefficient. The .join, strings, method is much more efficient because it allocates the necessary memory upfront. F-strings can be even more efficient but are only available in newer Python versions. Minimize object creation creating and destroying objects frequently can be expensive. Try to reuse objects whenever possible. In the inefficient _create _points function, a new point object is created in each iteration of the loop. In the efficient _create _points function, a single point object is created and reused. This reduces the overhead associated with object allocation and garbage collection. 4. Database optimization. Database performance is often a major bottleneck in applications. Consider the following techniques. Query optimization use indexes, optimize SQL queries, avoiding select using where clauses effectively, and profile query performance. Creating an index on the order_date column allows the database to quickly locate relevant rows without scanning the entire table. Using explain helps understand how the database plans to execute the query, revealing potential performance issues. Select only needed columns to reduce I/O. Schema design. Normalize your database schema to reduce data redundancy and improve data integrity. Connection pooling. Reuse database connections to avoid the overhead of establishing new connections for each query. Connection pooling reduces the overhead of repeatedly establishing and closing database connections. Caching. Cache frequently accessed query results to reduce database load. Consider using database caching solutions like Redis or MEMC8. This example demonstrates how to use Redis to cache user data. Subsequent calls to get_user with the same user_ID will retrieve the data from the cache, reducing database load. Expiration can be set to invalidate the cache after a certain period. Read replicas. Use read replicas to distribute read traffic across multiple database servers, reducing the load on the primary database server. Database partitioning / sharding. Divide large databases into smaller, more manageable partitions or shards to improve performance and scalability. 5. Infrastructure optimization. Optimizing your infrastructure can lead to significant cost savings, especially in cloud environments. Right sizing instances. Choose the appropriate instance sizes for your workloads. Over-provisioning can lead to wasted resources. Auto-scaling. Automatically scale your infrastructure up or down based on demand. This ensures that you only pay for the resources you need. Containerization. Docker package your applications into containers to improve portability, consistency, and resource utilization. Docker allows you to package your application and its dependencies into a container, ensuring consistent behavior across different environments. This improves resource utilization and simplifies deployment. Orchestration. Kubernetes. Use Kubernetes to automate the deployment, scaling, and management of containerized applications. Serverless architectures. AWS Lambda, Azure Functions, Google Cloud Functions use serverless functions to execute code without managing servers. This can significantly reduce infrastructure costs for event-driven applications. Serverless functions allow you to run code without managing servers, reducing operational overhead and cost. You only pay for the execution time of your functions. Spot instances / preemptible VMS. Use spot instances or preemptible VMS for non-critical workloads. These instances are significantly cheaper than on-demand instances but can be terminated at any time. Data storage optimization. Use appropriate storage classes, example AWS S3 Glacier for archival data, to optimize storage costs. Consider data compression and deduplication techniques. Content delivery networks, CDNs. Use CDNs to cache and serve static content, images, CSS, JavaScript, closer to users, reducing latency and bandwidth costs. 6. Development process optimization. Optimizing your development process can also contribute to cost savings. Agile methodologies. Use agile methodologies to deliver value incrementally, reduce waste, and adapt to changing requirements. Automation. Automate tasks such as testing, deployment, and infrastructure provisioning to reduce manual effort and errors. Code reviews. Conduct code reviews to identify potential performance issues, bugs, and security vulnerabilities early in the development cycle. Continuous integration / continuous delivery, CI/CD. Implement CI/CD pipelines to automate the build, test, and deployment process, reducing the time it takes to release new features and bug fixes. Technical debt management. Address technical debt proactively to avoid future maintenance costs and performance issues. 7. Monitoring and measurement. Monitoring your application's performance and resource consumption is crucial for identifying areas for improvement. Key performance indicators, KPIs. Define KPIs that are relevant to your application's performance and cost, such as response time, error rate, CPU utilization, memory consumption, and network bandwidth usage. Monitoring tools. Use monitoring tools such as Prometheus, Grafana, New Relic, Datadog, and AWS CloudWatch to track your KPIs and identify anomalies. Log analysis. Analyze logs to identify errors, performance bottlenecks, and security threats. Profiling tools. Use profiling tools to identify performance bottlenecks in your code and database queries. Cost tracking. Use cost tracking tools to monitor your cloud spending and identify areas where you can optimize costs. Cloud providers typically offer tools for cost management. 8. Case studies and real-world examples. Example 1. Optimizing a slow API endpoint. A company discovered that one of their key API endpoints was taking an unacceptably long time to respond. After profiling the code, they found that a database query was the bottleneck. By adding an index to the database table and optimizing the query, they reduced the response time by 90%, significantly improving user experience and reducing server load. Example 2, migrating to serverless. A startup migrated their backend API from traditional virtual machines to AWS Lambda. This eliminated the need to manage servers, reduced operational overhead, and significantly lowered infrastructure costs. They only paid for the actual execution time of their API functions. Example 3, implementing caching. An e-commerce company implemented a caching layer using Redis to cache frequently accessed product information. This reduced the load on their database and improved website performance, resulting in increased sales and lower infrastructure costs. Conclusion. Cost optimization is an ongoing process that requires a commitment from all members of the development team. By understanding cost drivers, implementing optimization strategies at different layers of your application stack, and continuously monitoring performance and resource consumption, you can build efficient and cost-effective applications that scale effectively. Remember that the most effective strategies will depend on the specific characteristics of your application and infrastructure. Regular analysis and experimentation are key to finding the right balance between performance, cost, and maintainability. Don't be afraid to revisit your optimization strategies as your application evolves and new technologies emerge. Cost remains an issue, a continuous and iterative approach will yield the best results.